Bismillahirrahmanirrahim. We'll now discuss the last segment on production of radionuclides, that is production using the generator system. These are the learning outcomes expected of this last segment of discussion. During the early days of nuclear medicine, radionuclides use had relatively long T-half, and this would give significant radiation doses to patients. For example, iodine-131 with 8 days half-life. When technetium-99m was made available, its use then was limited to nuclear medicine centers that are in close proximity to the production sites, which were the nuclear reactors supplying the centers of the nuclear medicine with TC99M. It was then available in solution form, ready to use TC99M sodium pertechnetate solution, where the half-life is a limitation. A solution to this challenge is overcome later on through the development of generator system. In a generator system, the long-lived parent radionuclide is loaded onto the column, and it continuously decays to the daughter nuclide, which are having a much shorter half-life. The challenge then is that there should be an easy method of separation of the daughter radionuclide from its parent. And the usual technique used is elution from the chromatographic column using a suitable liquid eluent in which the daughter can be eluted and the parent would stay onto the alumina column. Before that, various methods of separation were tried. First is precipitation, second distillation, such as the use of distillation to remove or to extract iodine-131 from tellurium-131. And at later stages, solvent extraction method were used for separation of technetium-99m from molybdenum-99 using methyl ethyl ketone organic solvent. Technetium-99m is more having a propensity to accumulate in the MEK solvent, and from which it is being dried and then redissolved to get technetium-99m pertechnetate. And the last method, which is the most popular, is the ion exchange or the chromatographic column that we have just mentioned early on. There are several types of parent-daughter pairs that have been tried in the development of generator system. Of course, the first type 1, where the parent is having a shorter half-life than the daughter, this is not a useful relationship to be converted into generator system. Type number 2, where the half-life of the parent nuclide is much longer than the half-life of the daughter. An example is the mercury-195, which is having a half-life of 40 hours, that gives the daughter gold-195m with half-life of 30.5 seconds. This kind of relationship of a much longer parent relative to the daughter gives what is known as secular equilibrium generator system. Type number 3, where parent radionuclide is relatively longer than the daughter radionuclide by just about 10 to 50 times. An example of this kind of relationship is exemplified by the molybdenum 99, which is having a half-life of 67 hours, and Tc99M with a half-life of 6 hours. This is the kind known as transient equilibrium generator system. In technetium molybdenum generator system, the technetium will be eluted at various time interval, and usually it is eluted once daily, and in order for you to get the maximum radioactivity of Tc99M from the molybdenum 99. There are several types of chromatographic generator system. One is the positive pressure, and the second is the negative pressure. You can read the positive pressure by yourself, and I'll go straight to the negative pressure generator system. In a negative pressure generator system, the eluent reservoir, which is depicted on the left, fitted with a one-way air filter, and the evacuated vial, which is placed on the right side of it. In between, you can see the alumina column, which is fixed in a suitable thickness of lead as a shielding material. When the evacuated vial is placed onto the connected to the terminal filter, it will withdraw the saline from the reservoir, and it passes through the alumina column, and together with it, it collects the technetium-99M into the evacuated vial. Other types of generator system, apart from molybdenum 99, Tc99M, you have mercury 195 and gold 195M. You have also rubidium 81 and krypton 81M. You have, among the recent generator system, is germanium 68 that yields the daughter gallium 68. This is a very interesting development. Germanium 68 yielding the daughter gallium 68, which is 68 minutes, and it is useful for positron emission tomography. So this is a depiction of the mercury 195, gold 195M generator, which was developed in 1984. Right? And for the rubidium 81, krypton 81 generator, you have the product nuclide, or the daughter radionuclide. Here is krypton 81, which is only 13 seconds, which has a very short half-life of 13 seconds. In a gas form, it can be used for studying the ventilation system. And this is the most commonly used generator system in nuclear medicine center, molybdenum Tc99M generator. It uses fission-produced molybdenum 99. I hope you can still remember from our previous discussion. Fission-produced molybdenum 99 provides a high specific activity of molybdenum, and it can be produced in high activity and requires small volumes of elution. During the early days of development, it uses the column remain full of saline between elution, which results in some radiolysis, but the later development produces dry column, which could be discussed during our class tomorrow. So regarding generator system, there are some quality control parameters that you need to conduct. Number one, to ensure or to observe the volume of elution, and number two, to assay for the expected activity, and number three is to conduct breakthrough of the parent radionuclides. And of course, it is important to ensure that the the elution is conducted under strict aseptic method. So this is an example of elution yields from several generator systems in one of the nuclear medicine centers. Yep, you can see based on the generator batch number, let's follow the last one, the last two, 090431. On 17th day of the month, you managed to elute 206 millicuries, and the following day, 24 hours after that, you can still elute 207 millicuries. Same, roughly the same quantity of technetium 99 and pertechnetate can be eluted. Problems that may arise with regard to generator system: you may have loss of vacuum from the elution coils. You may have presence of liquid in the dry column, we've just mentioned. And the third one, if you have channeling within the column material, then it's going to give you some other challenges as well. As a summary, generators are one of the sources of radioactivity or radionuclide that are used to supply short-lived radionuclides to distant nuclear medicine centers. Chromatographic system is most dominant. Negative pressure system is a fail-safe system. Thank you so much. Assalamu alaikum wa rahmatullahi wa barakatuh.